so start up again. Thanks. All right, so measuring reaction rates. And we're going to continue our earlier discussion of measuring reaction rates. We now have a couple more ways of looking at the rates of reaction. We saw that calcium carbonate can be, with heat, encouraged to break down into calcium oxide, that's a solid, and carbon dioxide gas. And calcium carbonate is a solid. So if we apply heat to a sample of calcium carbonate, we can get it to break down into calcium oxide and carbon dioxide gas. And what we're going to do is we're going to quickly look at ways of measuring the rate of this reaction. And you're going to give them to me. Yes?
Can you go down a little bit? Yeah, well, to the gut.
You're about there? Okay. Anytime. All right, so calcium carbonate, which is a solid in heat, is going to calcium oxide and carbon dioxide gas. Will the change in mass of the container help us measuring this reaction rate? If we have this in a sealed container. So we seal this all up. Can we measure its change of mass to get the rate of the reaction? If I put this all inside a sealed container, can I use the change of mass of that container to get the rate of this reaction? The change in mass. Can I put that whole thing on a balance and get the change in mass, and that'll tell me the rate of this reaction? No. No, why not?
It doesn't work that way.
You're right, why doesn't it work? Inside a sealed container, what? It's going to always be true. Total mass of products equals total mass of reactants. Now, if I have that container open to the atmosphere and I allow this reaction to go forward, can I use the change in mass to tell me the progress of the reaction? Yes, I can. Why?
It's reacting.
Yes, the carbon dioxide is going to leave the container because it's a gas. And so will the container be getting lighter or heavier as the reaction proceeds?
Lighter.
Lighter. So the rate of this reaction can be measured by the change in mass of everything, the mass of the container, over the change in?
Reaction.
Change in?
Time.
Time. It's always in the change in time. Now, for an open container, yes?
What's that arrow for carbon dioxide?
This is a little arrow that shows that the gas is evolved. It leaves, it goes off. That's chemical symbol for the gas is liberated from the reaction. If this is a closed container, I probably avoid putting that arrow in to remind myself that the mass is present. But an open container, I put the arrow in to remind you that that gas is what we say evolved. It just leaves the container. Okay? So the mass of the container over time, if it's open. If it's not open, then we can't use that. Are there any other masses that we can measure if we're going to measure individual masses that would help us? Can we measure the masses of individual components to help us tell the rate of the reaction?
Yes.
Yes, what components?
The container, does it have like what's in the container
Well, if we just, let's decide it's an open container. So we know the carbon dioxide is being leave. It's allowed to leave, sorry. What would be left back that we can measure? It's okay to call the names of the chemicals.
Calcium?
The calcium carbonate. Now, will the mass of calcium carbonate increase or decrease over time? Decrease, so we'll need a negative to keep that rate positive. The rate is also equal to the change in mass of the calcium oxide. Will that increase or decrease over time?
Decrease. Increase.
The calcium oxide increases over time, so we can leave the rate alone. It will be positive. Now, let's go back to a sealed container. We can't use mass, but what we can use in a sealed container, if it's flexible, is volume. Good. So sealed container, but it's flexible. Right? So the rate will be equal to the flexible sealed container. Yes. Now will the volume be going up or down over time as this reaction proceeds? You have a solid that becomes a solid and a gas. Gases sway it. Doesn't matter even if there's solid liquids and gases, solids and liquids present. It's the gas that determines the change in volume. Okay? So if there's a gas present, that's what determines the change in volume. You just count the amount of gas molecules on either side. It's nice to have it closer to the point. All right. So the volume is going up, so we can just leave it like that. What about if it's a sealed, inflexible container? What can we use to measure? We can't use volume now because the container is inflexible or rigid, so it's not going to expand with us. But that doesn't mean that the conditions in there aren't changing. Oh yeah, sealed inflexible container or sealed inflexible container. Thank you. So it's an inflexible container.
What does that mean?
It means the container is rigid and does not expand.
They're so
There we go.
Is
So
that
sealed,
negative?
inflexible container, a rigid container. Okay. Now, if it's inside this rigid container, obviously the volume is not going to change, but what will change inside the container as the reaction proceeds?
Pressure.
The pressure. So the rate will equal to the change in pressure. Will the pressure be going up or down as the reaction proceeds? Up, so we can leave it as is. What about the pressure of a specific gas? Can we use partial pressure here? Yes, we can. So the rate is also equal to the change in partial pressure of CO2 gas over time. We can use the whole pressure of the container because we know carbon dioxide is being evolved, or we can use the partial pressure of the one gas we're interested in. Same thing. If we have several gases present, we often want to use partial pressure because we get more rate loss out of it. Answer questions more easily. This is supposed to be unofficial, but in fact a comment. All right, so the masses work, the pressure work, there's one more thing we can use to measure. It doesn't matter if the container is sealed or open. This other thing we can use here. Temperature. Because this absorbs heat, we know that the temperature will change as the reaction proceeds. So the rate can also equal the change in temperature over the change in time. Do we need a negative here?
Maybe.
Is the heat going up as the reaction proceeds, or is the heat going down? The heat is going down, so we need a negative to turn it all positive.
Why are there two T's? Oh, temperature.
Lowercase t stands for temperature, uppercase t stands for... Sorry, I got that backwards.
Time. Lowercase time.
That's right. Keep me on my toes. Lowercase always stands for time. In this course, uppercase stands for temperature.
You are...
Who are you? You're at the front of the class. Now, if the reaction has other special characteristics, you can use those to talk about the rate. For example, some reactions produce a change in color, optical density, conductivity, pH or acidity, noise.
What's noise?
It's sound being evolved from a reaction. Some reactions produce sound.
Okay.
Light, some reactions produce light. Many of you have met this, you've gone to the amusement park and you get glow sticks. Well, that's just a chemical reaction in there. They got a base in one and a chemical called luciferin in the other. When you break it open, the chemicals mix and the energy doesn't come off as heat, it comes off as light. And you can actually measure the progress of the reaction by the light preceding. And over the course of the night, it gets less and less light because you use up your chemicals, so the reaction goes slower. And then some kids have found that if you want to make those glow sticks last even longer, you stick them in the fridge. Like, you know, you're going to go to bed, stick them in the fridge, slows the reaction down. When they warm up, the reaction speeds back up. So they'll last a little bit longer if you put them away. All right, your homework. Your homework is Hebden, page 3 to 5. And do exercises 6 through to 9. And that's all she wrote.